So let me open my presentation. Yes. Yeah, here it is. So, okay. So can you see the screen now?
Yes, all good.
Yeah, that's nice. So welcome again to our third day of the session. So it's 24th October and today's topic is controlling the NASA Microbservatory online telescope of your own and the image processing using the JS9 image processor. So I think both of these topics are quite new for all of us. So you'll be getting it in more detail stepwise. So it's all about controlling the telescope, okay? And this telescope is actually the remote telescope, so it can be operated online. So just you have to give the commands online and the telescope will click the image according to your command, according to the objects you selected. And again, the telescope will send back the image of the object you have ordered. So you can get your image back through the email. And once you have the image of any object, we can we can enhance that image by using a online software that is the JS9 image processing software. Okay, so I think before we directly get inside the NASA Micro Observatory online telescope, I would like to start from very basic. So we have to know few of the terms before starting. So I'm going to the third slide. So before we begin, we have some questions. So we can ask the questions to our students. So this is actually the opening discussion. So ask your students the following questions. The first one is, have they ever used a telescope before? And if so, for what? Okay. And the next is, in what ways is the telescope like their own eye? So I would like to ask you leaders first. So any of you have used the telescope before? Any types of telescope? The handmade telescope or any, the modified ones?
No.
So you have not used any type of telescope, right? It's okay. So today we are going to use the telescope, not the small one. It is the large telescope, but we won't be using it in real. We'll be using it virtually, that is online. Okay. So I have one small telescope with me. I just want to share with you. So this is a small tabletop telescope. And you can see over here, and I will remove the cap. So you can see over here. So it is the end from where the light is collected. This is the diameter or the aperture or the opening. And here is one lens, the the mirror, the primary mirror over here. You can see over here. I think you can see her reflecting. And at this point, we have a small mirror that is the secondary mirror. So the first of all, the primary mirror will collect the light from the object and it will focus that to the secondary mirror that is at this point inside this. And finally, the image is focused to this eyepiece you can see over here. So the final image will form at the eyepiece, and we can able to see the image by placing our eyes at the eyepiece like this one. Okay, so this is a simple telescope, the tabletop telescope. So with this telescope, I was able to see the craters of the moon, the lunar craters. I have also seen the moons of Jupiter. So I think we know 4 moons of Jupiter: Io, another Europa. Okay, so the 4 moons of Jupiter, it can be seen with this small telescope. And we can't expect much more from the small telescope. So we can't see the galaxy, we can't see the nebula, we can't see the star clusters. So we can't see the deep sky object with this small telescope. For that, we have to go to the big telescope, or the telescope which have high resolving power. Not only the resolving power, but there are several factors which makes the thing possible. So we'll be doing that later on. Okay, so after asking the students the questions that they have ever used the telescope before, so if yes, so which object did they see in the telescope? And the next one was, how is the telescope like their own eye? So it is like the similarity between our eye and telescope. So I'm going to hit the 3rd slide. So after asking that question, we can review with the students the basic similarities between the eye and the telescope. Okay, so let them say first, and then afterward we can just review it and tell them back. So the first point can be, both have an opening to let in light. Okay, so this is the diagram of our eye, the human eye. So here is the light coming from the distant object, and when the light enters inside this cornea, or we can say the pupil. Okay, so the pupil is the main entrance for light to get inside. And the light, after getting inside, it is refracted by the lens. So this is the convex lens, and the light are refracted. It is refracted. The light actually bends and meets at a focus. So this is the focal point. And when the light meets at a focus, and if the focus is on retina, then we are able to see the image. Okay, so I think all of us have some basic ideas about the working of the eyes, how eyes work. So in case of eye, this is the opening. The pupil is the opening. Okay, and this is the another diagram of the telescope. So we have one diagram for the telescope. So it has one mirror. This is the primary mirror at the base, and you can see this small one. This is the secondary mirror. So the lights, the parallel lights from the star, first strike on the primary mirror, and afterward the light is focused at a point where we have kept the secondary mirror, and again there is another refraction, and the final image is formed, which can be seen through the eyepiece. Okay, so here is the opening. So you can also see in this telescope. So this is the opening. This is the entrance for the light to come. So the light can gather inside through this. Through this opening. Okay. So this is one thing common in case of the telescope as well as our eyes. So both have the opening to let the light come inside. Right? Okay, the next similarity can be, so both focus light to form an image. So all of us know when minimum of 2 lights after reflection or refraction, okay, intersects each other, the image is formed at that point. Okay, so we can also say when the 2 lights intersect to form an image, then we can say that but the focus light to form an image. So the eye uses a lens. Here we can see this one is the crystalline lens. This is actually the convex lens, but it can change its focal length. Okay, it can be stressed with the help of ciliary muscles, where it can become thin as well. It can become thick. Okay, so it has variable focal length. So we have this lens that collects light, which gets inside our eyes. And next is the telescope. So telescope focus the image with the help of mirrors. They can also have the lenses, or they can have the combination of both mirrors as well as lenses. Okay, so in case of the Galilean telescope, we can say that there is lens at the main opening. Okay, so there is the convex lens, we call that objective lens, and at the another end there is the eyepiece, there is the another convex lens. Okay, so in case of Galilean telescope, there are lenses instead of mirror. But in Newtonian type telescopes, or we can say in refractive telescopes, we have the mirrors. Okay, and now in modern type of telescope, we have combination of both. So the lenses as well as mirrors, or the both, are used to focus the light. So I think, are we getting it? Am I audible to everyone? Yes. So if you have any question, we can ask each other. So I think Ibra has raised his hand. So do you have any question? Then please. Reza?
Yes.
Am I audible? I think it feels like
Yes.
I'm okay. So I'm not getting any response from the teachers.
Well, audience are not allowed to unmute themselves. You can check the chat. There were a couple of responses saying that they were able to hear you, and they're all good.
I'm still here, and they are answering in the chat, which is very good. So can you see, you can't see the chat where you are. All right, Reza, so you need to keep telling Niraj.
Yeah.
People are saying yes, okay.
So the next thing is, so both have the light detector to sense the image. So this is very interesting. So let's see the image of the human eye. This is the pupil from where the light gets, the light enters into the human eye. And when the light is focused or at a point on retina, so this is the enlarged image. So our retina consists of different cells. There are many cells, among which the two are of great importance. The first one is rod cell, and another one is cone cell. Actually, this part belongs to the biology, but we need to, as a physics teacher, we just need to know the names and what it does is, okay. So the main use of rod cells and cone cells is to make the image visible to us. So the rod cells and cone cells help us to provide the color. They helps to see the image. Okay, so when the image is formed, it is, you can simply say that it is processed by these biological cells, the rod cells and cone cells, and after that in the form of signals. So the image, the final image, which is formed on retina, so it gets converted into the signals, which is carried through this optic nerve to our brain, and finally the brain analyzes that, and we are finally able to recognize what is in front of our eyes. So finally it makes sense. So if unless the electrical signals don't reach the brain, we are not able to recognize or see what is in front of our eyes. Okay, so these cells are very important, and we can see them as a sensors. So they are the biological sensors, and these sensors help us to collect the light that is focused on retina, and finally we can interpret the image in our brain. So these rod cells and cone cells, I think we can say it uh, as a light detector, right? So it is the biological light detector. So just come in case of telescope. So we have actually in any telescope we have two parts, the objective and the eyepiece. So when the light from the objects gets inside this, and this is the primary mirror, so we can call it objective. And another lens, this is the lens through which we see the final image with the help of our eyes. Okay. So this is the eyepiece. We use eyepiece when you need to see the image directly with the help of our eyes. But what happens in the big telescope, in the observatory? So we don't have enough time to sit by the eyepiece and see it continuously. So in that case, we use a camera. Okay, so there is a special type of camera that mainly we use CCD camera, that is the charge coupled device, or you can also use the DSLR camera if you are amateur photographer like this. This is a camera, DSLR camera. So what we have to do is we have to remove this lens. So this is the lens. We can remove this lens, and now you can see this. So this is the body, and there is a sensor. So there is the sensor inside it. Okay, the CMOS sensor. And what astronomers actually do is they fit one adapter. So actually I don't have adapter right now. So we fit the adapter in this part, and the another end of adapter is fitted, or it is coupled to this section of the telescope. We can remove the eyepiece of this telescope, and after removing the eyepiece, you can couple the camera. Okay, so now it will act like this one. So like this. So now the camera, the sensor of the camera will capture the image which is received by this telescope. So I think we are getting it. Okay, so the sensor of the camera will act as the retina. Okay, so in case of our eyes, the retina are responsible for the formation of the image. Okay, so when the image is formed at the retina, we are able to interpret that image. So the cells on the retina act as a biological sensor. In the same way, in case of telescope, we have the camera attached to it, and the sensor, the CCD sensor or the CMOS sensors are used to collect the light. Okay, so when the light falls on the sensors, then we can say the images are recorded, the image is formed. Okay, so these were some of the similarities between the human eye and the telescope. Now we have some questions. How does my eye compare to the telescope? So there is comparison between the eye and the telescope. The first one is, everyone knows that a telescope helps to see us better. Yeah. So this is all of us know that the telescope helps to see us better. But why? How does it? Okay. So this is the main question we can ask to the students. So why the telescopes are used to see the distant object better in comparison to our eyes? The next question can be, which features of a telescope make it such an important tools? Okay, so what are the features of the telescope which makes the telescope such a helpful device that we can see the objects billions and billions of kilometers, the light years, okay, which can be easily seen with the help of an advanced telescope. So what are the features of telescope that makes it's so important tool. The next one is, what can the eye do that the telescope can't? Okay, so there are some benefits of eyes as well. Okay, but here we will deal much about the important aspects of the telescopes. Okay, so relating to our eyes, comparing to our eyes. So now the purpose of this exploration is to compare the performance of our own eye with the performance of NASA Microbservatory online telescope. So different telescopes have different specifications. Okay, so they have different features. But today we are going to control the NASA Microbservatory online telescope. Therefore, I think we can compare the performance of our eye, our naked eye, or we can see the unaided eye with the NASA Microbservatory online telescope. So let's start with the comparisons. The first comparison is size of the opening. So you can see the image of the eye over here. So it has different parts. You can see this round, the black round shape. So this is the pupil. So it is the main entrance. It is the door from which the light gets inside our eyes. Okay, so this black area, this is the pupil. So the first comparison is size of the opening. We can say pupil. Here the pupil is the opening of the eye. So what is the size of the pupil? So we can start by some activity like measuring the size or the diameter of the pupil. So have the students look at the pupil of their partners, of their friends. So the pupil is the black opening in the center that lets in the light, and students should observe the size of their partner's pupil and measure the width of this circle using the ruler. But it is very risky. Okay, so it should not be performed with the students alone. So there must be parent or the teachers with the student, so that they don't get the ruler or any sharp object inside the eyes. So I will not recommend this to do for students without any proper guidance. Okay, so you can help the students. Actually, we don't need to put the scale or the measuring tape very close to our eyes, but you can measure it roughly. Okay, from by maintaining some gap or the distance between the eyes and the ruler. But I'll say the value, I will say the measurement of what the average adult size of the pupil is. Okay, so better is not to perform this activity with the students without the proper guidance. So I will say that the normal pupil size of the adult varies. Okay, so it goes on changing. So there is the variation. So it varies from 2 to 4 millimeter in bright light. Okay, so when the light is enough, when the light is where there is bright light, then we don't have to open our eyes more. Okay, you can see the things clearly within the small area. Okay, with the small opening actually. So when we have enough light, then 2 to 4 millimeter of opening is enough to see the objects clearly. But when it is dark, okay, so when it is the evening time, you don't have the proper lightings. In that case, in order to see the image clearly, we have to enlarge. We have to enlarge the opening. So our eyes does that automatically. You don't need to adjust any things. Okay, so it is just the autonomous process. So in that case, in dark, the size of the pupil grows from 4 mm to 8 mm. So it is the average value. So this is not the case of all age groups. So all age groups won't have the same size. So this is the average size of a normal adult person. Okay, so for a normal person, for a normal adult, these are the value. So 2 to 4 mm when it is bright, and 4 mm to 8 millimeters when it is dark. Okay, so let's take the maximum size of the pupil that can be expanded. Okay, so we can expand our pupil size maximum up to 8 millimeters. So when I convert this 8 millimeters into centimeter, we can divide it by 10, so we'll get 0.8 centimeters. Okay, so the maximum pupil size for average normal person is 0.8 centimeters. Now let's see what is the size of the opening of the NASA Micro Observatory telescope. Okay, so here we go. So here is an image of the telescope. This is the NASA Micro Observatory telescope. So it has been installed in open place, and this is the main body of the telescope. And you can see here the opening. You can see the round opening. Here is the opening of the telescope. So these are the arms of the telescope. So I think this is the cable. Okay, so the telescope are free to rotate. So it can both flip horizontally as well as it can have the vertical movements. Okay, so these arms keep the keeps the telescope to move 360 degree around. Okay, so this is the main opening of the NASA Micro Observatory telescope, and it is so the size is fixed. I must tell you that the size of the Micro Observatory telescope opening is about 6 inches wide. So it is not in centimeter, it is 6 inches. Okay, so the telescope that I have, you can guess the size of this telescope. So this is about 4.5 inch. Okay, or might be 4 or 4.5 inch. Okay, I didn't remember this actually. So the NASA Micro Observatory telescope has its opening about 6 inches. So when I convert, so we have the conversion factor, 1 inch is 2.54 centimeters. So the 6 inch will be the product of 6 and 2.54, that is 15.24 centimeters. Okay, so here we have the diameter. This is actually the diameter of the opening of Micro Observatory telescope. So now we are going to comparing the diameter of the human eye and the diameter of the Micro Observatory telescope. So before we do that, again we can ask our student questions. So have the students compare the size of their pupil with about how many times more light does the telescope opening let in compared to your eyes. Okay, so to say it simply, so we have to compare by how much amount. Okay, by how much amount the telescope receives more light in comparison to our eyes. So since the diameter of the pupil was how much, 0.8 centimeters. Okay, but the diameter of the opening of the Micro Observatory telescope was about 15 point something. So what was it? It was 15.25. So since the opening of the telescope is more in comparison to the human eye, so I think all of us can say that the telescope will collect more light. Okay, so now the question is, how much light does the telescope gathers in comparison to the human eye? And we are going to answer these questions, or we can say you will let your students decide first which is the relevant features, the width of the opening or the area of the opening. So what should be compared? Should we compare the diameter of the NASA Micro Observatory telescope divided upon by the size of human eye, or should you go for the area, or should we compare the area of the opening of Micro Observatory telescope upon the area of the human eye. So let the students say first, so which feature is relevant, the width or the area? After that, we can say them that the area of the opening is important factor, because when the light enters the telescope, so it uses the whole area. Okay, so the whole area is responsible for collecting the light. And you can see here the opening is circular in shape. Yes, so mostly all the telescopes have the circular openings. Okay, so the Microbservatory telescope has also the circular opening, as well as the pupil of our eye, so it was also circular. Okay, so for the area of circle, we have the formula area of the circle as pi r square, and since the radius is half of the diameter, so pi d by 2 square, and finally we will get the area pi d square by 4. Sorry, there is one mistake, so I can't write a proper symbol of pi over there, so it was missing. So see over here, if the maximum diameter of the pupil, that is 0.8 centimeter, then what would be the maximum area of the pupil? Okay, so the area will be pi d square by 4, and I will say all of you to calculate this with your own. We can put the value of pi as 3.14, or you can go for you can take is 22 by 7, and the diameter is here 0.8, the square of the diameter, and this is divided upon by 4. I guess I have calculated it correctly. So the area came to be 0.5024 square centimeter. So I will pause for a minute, and I'll ask you to check this, whether the area I have calculated is correct or not. So before that, I will also tell you the diameter of the Microbservatory telescope, the diameter of the opening, it is 15.25. So again, you can use the maximum area of the telescope opening. You can take is pi d square by 4. I'm denoting the diameter of the eye by small d, okay, the small case, d in small case, lowercase, and the diameter of the telescope by capital D. So it will be helping to distinguish from each other. So just use this formula, pi d square by 4, and given are the diameters in centimeter, and let me know whether the area that I have calculated is correct or not. So I will pause for 1 minute, and I'll be waiting for you.
Hello?
Yes.
Is correct.
Yeah. So the
Your
area for the
calculations are
pupil
correct?
is correct?
It is correct. Hello? Your
Okay.
calculation
And
is
what
correct.
about the area of the telescope opening? It is correct? Great. Okay. So if it is correct, yeah. So if it is correct, I will go to the move to next slide. Okay, so now, yes, so now I need to, what happened? Just a minute. I'm not getting. Yes. Now. Okay. So sorry, it was difficult moving from one slide to another. Now we can compare the area of the pupil and the area of the telescope opening with this mathematics. So 182.1, this is the area of the telescope opening. I think I have made one small mistake over here. So this would be first. So maximum the area, I think the area of telescope would be at numerator size, area of the telescope. And when the area of telescope opening, this is divided by maximum area of pupil. So this is the area of the telescope and this is the area of the pupil. So when we will divide these two, I think we'll get 363.378. So approximately it is 363. So it doesn't have any unit because it is the comparison. So the centimeter square and centimeter square cancels each other. So we have 363. So what we conclude from this, so the NASA Microbservatory telescope gathers about 363 times as much light in comparison to our eyes. So am I correct? Is that interesting? So from the small mathematics, we're able to find how much the light is gathered with the help of NASA Microbservatory telescope in comparison to our human eyes. So when you see a object, the faint object, the object that is very, very distant away from us, then we won't be able to gather much more light from that distant object. Okay, but if we are using the telescope, so the telescope will help to gather more light in comparison to our unaided eye or the naked eye. So it is something like 363 times. Okay, so this NASA Microbservatory telescope allows 363 times as much light as our naked eye could have collected. Okay, so I think this was simple, but the result or the conclusion is interesting, so we can share it to our students. So do we have any questions for the comparison first, for the first comparison? If not, then we'll move to our second comparison. So shall I move to our second comparison, or do we have any questions? Okay. So let's start our another slide, that is comparison 2, that is exposure time. So what do you mean by exposure? Okay, so exposure time is actually the time for which the light is collected to the sensor. Okay, so what happens in the case of the telescope camera?
I wanted to find out. Why don't we make the diameter of the telescope infinitely wide? Because it is clear that the wider the diameter, the more the amount of light that enters. So why do we regulate it? Does it affect picture quality?
Yes. So actually the telescope having the large diameters or the large aperture collects more light. Okay. So your question is, why don't we build or construct the telescope having very large aperture, right? So we do. Okay, but it is not possible in all the cases. Okay, so the large telescope always have the big diameter. Okay, so but there are several factors that restrict to make the telescope having the narrow diameter. The first one, if you are using the lens as an objective lens, then it is very tough to make a large lens. Okay, so making the large lens is very tough. It is the technical problem. Okay, it is very difficult in making the large lens. And if you will buy a telescope having the large objective lens, I'm sure it will cost you much more. So simply we can't afford the telescope having the large lens, okay, convex lens. So the primary mirror was the option. So there were several benefits of using the mirror over the lenses. The first one was it is easy to construct the large mirrors as compared to the lenses within less expense, okay. And another thing is the chromatic aberrations. So the lens suffers from the chromatic aberration. It is just like when the image of the object is formed, the boundary of the image appears to be multicolor, okay, due to the diffraction of the light, okay. And so there are different colors like the red, green, blue appearing at the edge of the image, okay, in case of the lenses. But in case of mirrors, there is no chromatic aberrations, okay. So this is the another reason why we are using the mirrors, okay. Yes, so your question was why don't we make the large apertures? So it is always wise to make the large aperture, but it is very difficult, technically difficult to make the large telescope for the general purpose, okay. So if we are using the telescope with very large aperture, it will be much more bulky, it will be hard to carry, it won't be much more portable, okay, and there may be risk of damage from transporting from one place to another place. So there are several reasons why we are not using much more the telescope having much more diameter or the aperture for our daily use. So is the answer okay, or should I explain much more? And it is not only the diameter which is responsible for the final image, okay. So there are several other factors. There are the exposure times and various other factors. And I think the telescope with 6 inches, 8 inches, or above 10 inches are much more sufficient to see the distant object like the galaxies, the nebulas for the general purpose, okay. So the second comparison is the exposure time. What is the exposure time? In case of the camera, the shutter, there is a shutter. I wish I could show you right now. Okay, so can you hear this sound? When I click this camera, you'll be listening a sound like click. Okay, so what is this sound? Okay, this is actually the shutter. So there is a shutter in case of the camera that we use in our daily life, as well as the camera which are attached with the telescope. So actually the shutter allows the light when the shutter is open, it allows the light to hit inside the sensor. The light hits inside the sensor, so it hits the sensor, okay. But when the shutter is closed, so when the shutter is closed, it is just like the door, okay. So when the door is closed, nothing is able to come inside, okay. So when the door is open, the things can get inside, okay. So in the similar way, the camera has the shutter. So when the shutter is open, the light gets inside, okay. So this shutter, so the time for which the shutter is open, so that light can enter inside the camera and get to the sensor, the time is called the exposure time. So there would be one question: why should we put the shutter? Okay, what will happen if there is no shutter in our camera? Okay, so in that case, what will happen? The light will fall on the sensor continuously for long period of time. Okay, so when it is like that, the image, the final image, could be overexposed. Okay, so if more and more light gets heated on the hit the sensor, then the final image may be overexposed. Okay, So for that condition, we have to restrict the time duration of the light. So if the light is very bright, then we don't need to open the shutter for much more time. Okay, so if the source, the light coming from the source is very bright, then the fraction of second is enough. Okay, so if you will not, if you will allow the light from the bright source to pass through your shutter for the long time, then the final image will be overexposed. Okay, but in case of galaxies which are very far away from us, which are very faint, okay, so for that type of objects, we need to open the shutter of the camera for the long time, so that more and more light could get inside, strike the sensor, and the final image will be good to see. Okay, so the final image will be bright, not much more overexposed, but it will be bright enough that we can see the distant object, the faint objects clearly. So I think we have done talk much more about the exposure time. So the micro observatory telescopes, light sensing camera. Yes.
Excuse me.
Yeah.
Can you explain a bit? Can you explain a bit more about the image being overexposed? What is the disadvantage?
Okay. Okay. So I'll let you know. So overexposed means, okay, just take your camera. Okay, so just your tablet, and point the tablet to the bulb. Okay, to the bulb from where the the bulb is bright. Okay, so much more light is coming from the bulb. So when you point your tablet, the camera of your tablet to the bulb, and then you click the picture, so what will the picture be like? So the picture will
There
be
is some background noise.
Yeah.
Some background noise. Some please. Can that person mute, please?
Yes. Okay, I'll give one example. So just like there is no much more enough light facing to me, so I am looking a bit dark, okay, right now. But what if I will point the light on my face like this? You can see here. So I have used this torch light, and if the light is coming to me, you can see this portion of my face is overexposed. You are unable to see this part more clearly. Okay, so this is overexposed, and if I cover the light coming to my face like this one, like this, I'm not getting it much more correctly. So this portion, you can say that this portion is not visible, much more visible. So this is underexposed. Okay, so the part where the intensity of light is not much more, so that is the underexposed, and the portion where there is too much of light, that is overexposed. So was I able to explain you?
Okay, you have tried, but I was imagining that where you have got too much brightness would maybe depend on the diameter of the eyepiece, or I mean of the lens that you are using, because that's when it allows a lot of light to go in. But to do with exposure,
actually we have the shutter in every lens. Okay, we have the shutter in every lens. So unless I am clicking this one, so if I have not clicked this one, the door is closed, the shutter is closed. Okay, so when I click this one, it will allow the light from the source to get inside. So I can control the shutter speed. So there are some functions in the camera where I can control the shutter speed. So I will make the shutter speed fast. That I mean to say that the shutter opens and shut down much more fast, than very few lights will be able to get inside. In that case, the final image will not much more, will not have much more intensity. Okay, so that is poorly exposed, or we can say it is underexposed. So the final image can't be seen much more clearly, distinctly. Okay, So if I have the long shutter speed or the exposure time, so if I set the exposure time to 40 seconds, then what will happen when I'll click the camera button, so the shutter will open and it will remain open for 40 seconds. So till 40 seconds, the light will continuously get inside the sensor. So let us now imagine if the source was much more bright, okay? In that case, the 40 seconds, so the door is open, the shutter is open for 40 seconds. So in that 40 seconds, more than enough light gets inside the camera, and the final image on the sensor will become overexposed, okay? So overexposed is also not good, underexposed is also not good. So there must be the optimum quantity of light that is needed to see the final image much more clear, brighter, okay? So did you get me now? So it is not about the
Oh, okay,
defect of
thank you.
the lenses, it is just about the shutter, okay? And that can be controlled by
Okay.
ourselves in case of camera.
Would that be the same as saying that?
Can you say it again? Can you say it again? I didn't listen it completely.
What I'm saying,
Yeah,
would overexposure be the same as the image being blurred?
not black. The
Not
overexposed will
not
make the
not black,
image
but
white.
blurred, not seen clearly.
Yes, yes. So it is not seen clearly. Both the overexposure and the underexposure, both are bad. Okay. In both the cases, we want
Okay.
to be able to see our image clearly. So the main difference is when the image is overexposed, we have the dark shades.
Okay. Okay.
When
Thank
the
you.
image is overexposed, then we can see all the white things on the image. Okay. So both cases are bad. Okay.
Okay. Thank you very much for that explanation, sir.
Welcome, welcome. So the Microbservatory telescope light-seeing camera has the shutter which can open from 0.05 seconds to 60 seconds. So there is a range for this Microbservatory telescope. I'm not telling this, all the telescope will have the same exposure time in between this, but the Microbservatory telescope, okay? So this telescope has the exposure time that ranges between 0.05 seconds to 60 seconds. So depending upon the purpose, what type of objects we are trying to get the image of. So if the object is very faint, then we can increase the exposure time, okay? But we can't go beyond 60 seconds. And if the object is very bright, like if you are going to take the photograph of the sun or the moon or the full moon, okay? Then I think there will be much more brightness, okay? So that we have to reduce the exposure time, right? So this telescope, the exposure time ranges between 0.05 to 60 seconds. So longer the exposure time, the more light that the telescope can gather, okay? So if the exposure time is more, so if the shutter is open for more time, for more seconds, then more light will gather to make this image. Okay, I'll move to another slide. Okay. So now let's relate it to with our eyes. So actually our eyes don't have any shutter, okay? So you can think that the eyelid, this is the shutter, but actually it is, if you keep it open, okay? Then I think if you can control that you don't blink your eyes, then you can then the light can be collected inside our eyes for the long time. Okay, but there is one biological phenomenon. There is, I can say that there is a limitation. So what happens that our eyes, okay, when the light enters our eyes, and once the image is formed on retina, that image will last for, that image will remain for 1/15th of a second. Okay, so 1 second divided by 50, 1/15th of a second, for very, very small time. So it is the time the eyes will take the signals, it sends the signals to your brain, okay? And the fraction, this fraction of second is roughly the time which takes the nerve cells in your eyes and the optic nerve to gather the light, fire it, conduct an electrical signal to the brain, and prepare themselves to be ready to fire again. Okay, I'll tell it simply. So once the light gets inside our eyes, it forms the image on the retina, and that image is sent to our brain in form of the electrical signals. Okay, and again the brain interprets it, and we are able to see that image. Okay, so it just takes so the whole process takes less than 1/15 second. So I must say that our eye is ready to take the another image after 1/15 second. So we can say that one image can remain on the retina of our eyes for 1/15 second. So after 1/15 second, it is replaced by another image. Okay. So we can say that the exposure time for our eye is 1/15th of a second, that is 0.066 seconds. So it is very small. So this very small fraction of time is the exposure time for the human eye. So do you have any question regarding this? So there is nothing like the shutter or the shutter speed, but it is a biological process that the image automatically changes, okay, after 1/15 second. So one image can remain on your retina for only 1/15th of a second. So we can say that exposure time for our eye is 0.066 seconds. Now, here I'm going to compare the exposure time of the eye and the exposure time for the micro-observatory telescope. Again, I have done the same mistake. I should have written this one in the numerator. So the exposure time of the micro-observatory telescope, it is divided upon by exposure time of our eye. So it is 60 divided upon by 0.666. So I have taken the maximum exposure time. So it was like 0. How much it was? So it was 0.05 seconds to 60 seconds. So 60 seconds is the maximum exposure time. So I have taken the maximum exposure time. So 60 divided by the exposure time of our eye. So it is about 909.090. So we can take 909 approximately. So that is the second conclusion. So the second conclusion, the second comparison of the exposure time is the NASA Micro-Observatory Telescope gathers light about 909 times longer than the eye. Okay, so it collects the light for 909 times greater, much more, about 909 times greater than that of the eye for a single image. Okay, so to observe the very faint objects such as the galaxy, you must use the longest exposure time, that is about 60 seconds for this telescope. So these are the reason why our unaided or our naked eyes can't see the distant objects like the galaxies. Okay, so since the exposure time of our eye is very small, it is only 0.066 seconds. So this time is very small to gather that much amount of light that could form an image that can be seen clearly. Okay, so we have to go for the long exposure time that we do with the help of a telescope, right? So here we have the conclusion. The micro-observatory telescope gathers 909 times much more light in comparison to our eyes. So is that okay? So shall we move for the third comparison? Or do we have any questions? Let me know.
Yes, we can move on.
Okay, thank you. So our third comparison is the sharpness of vision, or we can say it resolution. So this is a very common term. So when we buy any mobile phone, mobile device, when we look for the camera, then we often ask what is the resolution of the image. Okay, we say that it is 3 megapixel, or we say this is 7 megapixels. Okay, so the higher is the megapixels, the high resolved image we can get from. Okay, so the sharpness of the vision, or we can say the resolution. So this is the third comparison. And to compare the sharpness of vision of our eye, we have got a small activity. So we can do the activity with the students, and we can also calculate how sharp vision does our eye have. Okay, so let's take a look. Prepare the experiment. So the punch 2 pin hole through a square aluminum foil about 1 by 8 inches apart. Okay, so you can get some aluminum foil, or you can also use cardboard paper that is opaque. Okay, that will not allow the light it shouldn't be transparent. Okay, right? So we can also use the aluminum foil like this. Okay, so this so the aluminum foil will not allow the light to pass from this side to this side. All the lights that strike on this side will bounce back or will be reflected back, right? Now, so we have to make 2 pin holes. Okay, for that we can take a box like this one. So this is a box, and you can cut at this cut this area with the scissors or knife. You can cut this area. You can paste the aluminum foil over here, or you can use the cardboard that is not transparent. Okay, so at one end we can do like this. Okay, we can we have to cut it out and then paste the aluminum foil, and at next end just cut that much so that you can insert a torch light. Okay, so this is a torch light, and we can so just cut that portion so that the torch light gets fitted inside. Okay, so now we have one idea. We have got the idea. So from one side we are going to illuminate with the help of torch light, and the another part, when it is cut, we have the aluminum foil. Okay, now make 2 holes on the aluminum foil. Okay, so we can make the 2 holes with the help of a pin. Okay, and the what should be the distance between the 2 holes? So it would be approximately 1 by 8th of an inch. Okay, so 1 divided by 8, you can calculate it yourself. You can convert inch into centimeters. Okay, and then you can put the 2 holes. We can make the 2 holes at the distance of 1 by 8 of the inches. So 1 by 8 inches apart. Okay, now what we have to do next is, while you hold the flashlight, have the students stand as far as possible from the flashlight. Okay, so you can do this activity at the corridor. If you have long corridor in your school, at your homes, then let one of your student hold this box, okay, with a flashlight, and let the other student stand at the far end, at the other end of the corridor, right? So make sure there is long distance between the source, that is the flashlight, and the student who's the observer, okay? So what we have done till now, so we have made two pinholes. The both pinholes were 1/8 inch apart from each other, and the two holes were illuminated with the help of a torch light. Now the light will come from both of the holes, right? And it act as a secondary source. So the flashlight will be the primary source, and it gets fitted inside the box, and at this end we have two holes, so the light will come from the two holes, right? So the two holes will act as a secondary source. Now just imagine that they are the two stars, okay? So the two holes represent the two stars, and the two stars are about 1.8 inches apart, yes? And we are going to see these two stars from very far end, okay? The student who is standing at one end is going to see the two holes, or say the two stars, okay? Now what you will find, so first do this activity with the students. So the first thing is, if the distance between the student and the flashlight is much more large, okay, say that 40 feet, 50 feet, then what do you guess? Will this student be able to see the both holes, or the light coming from both the holes, as two separate objects? Or will they, or the student won't be able to distinguish between the two holes? What do you think? Or you can imagine the similar situation that happen in your daily life. Can you give me the example of the similar things? Okay, I'm going to let you imagine a situation. So imagine just a car, okay? The car with the two headlights on. So the two front headlights of the car, okay, are on, and the car is approaching towards you. So it is coming towards you from the far distance. So when the car is 100 feet.
One example.
Yes. So when the car is very far away from us, we won't be able to distinguish, we won't be able to separate both of the light sources, right? So it will act as both of them are coming from the same point. So we'll think that it is not a car, rather it is a motorbike, okay? So it is coming. But as the car approaches comes near to you, it comes closer and closer to you, then only we can see that the lights are separate from each other. They are not a single source, rather they are the separate source. And as it comes approaches near and near, we will be able to see the both objects distinctly clearly, okay? So I think we have
Another example.
Yes.
Another example could be along a highway. When you have a
Yes.
straight highway with lights on both sides, when you're at a distance and you're moving, it may look like those lights are from a common point, but as you push closer, you find those lights are on either sides of the road.
Yes, very good. Yeah, that is another good example. Yes, thanks, Santos. Yeah, so that is the great example. So now we have the examples, we have related this problem with our daily life problem. So I think the student will feel the same like that, okay? So if the distance between the flashlight and the student is more than 50 feet, the 40 feet is more than 40 feet, okay? So I think he won't be able to distinguish between the two pinholes, okay? Now what we need to do is we have to tell our students to come closer and closer to the flashlight. Or we can do the observer remains still and the person carrying the flashlight will come closer to the student. Okay, we can do any of the two. So just try it. Okay, I think for a young adult, for the normal eye, the eye which don't have any type of defects like the myopia, the hypermetropia, so nothing like that. For the average adult, the distance from which you would be able to distinguish the two objects which are kept at a distance of 1/8 of an inch. So there is a calculation, there is the mathematical calculation for that. So it is found to be 35 feet. Okay, so I can show you in another slides. So this is bit experimental and it has been proved mathematically. You can also do that. So you can repeat the same activity and you can also check whether this results fits in your case or not. So when the student is approximately 35 feet away from the flashlight, and when the 2 points are 1/8 inch apart from each other, then the student will be able to distinguish when it comes when the distance between the student and flashlight is 35 feet. Okay, so just repeat it in your case, and I'll say that every student don't have same power of vision. Okay, so it may differ from person to person. So here the 35 feet is for the average normal eye, okay, for the normal eye, and it is the average value. So for some students it can go to 30 feet, so some will be able to distinguish when it is 37 feet. So it may vary from case to case, but here I have taken the average value. Okay, now so I'm going to relate this value with the micro-observatory telescope. Okay, so in the case of micro-observatory telescope, what it has been found that if the two objects are separated by the same distance, that is 1/8 inches apart, then with the help of this telescope, you will be able to differentiate the two sources distinctly at a distance of 875 feet. So I mean to say, when the object is 875 feet apart from you, then with the help of this NASA Micro-Observatory telescope, you would be easily able to distinguish the two light sources. Okay, so just for comparison, how we can compare is, again, divide 875 by 35 feet, you will get about 25. Okay, so we can say that the NASA Micro-Observatory telescope has 25 times better sharpness of vision, or you can say that it has 25 times better resolution than the human eye. So I will say that we can repeat this experiment with the students, okay, and just find it out what is the resolution of student eyes, what is the resolution of our eyes. Okay, so is that okay? I'll pause for a time. I want to discuss with the with the teachers. So do they have any questions like for this activity? So teachers, kindly tell me. So will it be easy to perform this activity in the classroom?
Yes, I think that experiment is interesting.
Yeah.
The only thing is, you said the two pins or the holes should be 1/8 apart. 1/8 of an inch.
1/8 of an inch.
Yes, 1/8 part of 1 inch. So I have to keep one reference, right? So in both the cases, so in case of our eye, as well as in case of the micro-observatory telescope, so we have to take a reference first. So 1/8 of an inch, So I have just taken as a reference. Okay, you can take it you can, as your wish. So you can take, I think you can take 10 centimeters. The two sources are 10 centimeters apart. Then what you have to do is you may take a long distance, okay, more than 35 feet. I think in this case, the distance will grow larger, okay? So in both the cases, I have kept one reference that is 1/8 of an inch apart. So in that case, your eyes will be able to resolve at a distance of 35 feet. So if I'm going to change this one, so if I'm going to increase or decrease the distance between the two objects, then of course, the distance from the flashlight and the observer will change.
I just want to appreciate this experiment here.
Yes.
I think it is a very nice way of introducing the concept of image resolution to students.
Yes, thank you. So since I have found this data in the website, so there was like the micro observatory in case of micro observatory telescope. So if the distance between the two objects is 1/8 of inch apart, then it will be 875 feet. Then the distance to see the image clearly would be 875 feet. Okay, so that's why I have also included the same reference 1/8 of the inch. Okay, so you can differ it. If you will differ it, you will get the distance at which the two images are resolved, the separate distance. You'll get the another distance.
Hello.
Hello. Hello. Yes, I'm listening you. So, do you have any questions?
Hello.
Hello, I think you have the network issue.
Yeah, just for both.
Can you write the question in the chat? So, there's more in the chats. So, I think there was the network issue and Pascal was unable to put his questions. So I think he can do it some other time. So how to get this chat off? Okay. So shall I move to the next slide?
Yes, you can.
Yeah. So I think this was the last slide for the before we could start the real observer, the online observation, or we can say you can control the telescope online. So now we are moving towards controlling the NASA Micro Observatory Telescope. So just watch the steps carefully. It is very simple steps, and after you get through all the steps, you can try and control the telescope of your own, and you can also order the image. So it will be quite interesting. So it is very small process I'm going to show you, and after I finish, you can try it just now. Okay, so I'm now going to Google search. So if you, so the name of that telescope is NASA Microbservatory Online Telescope, okay? And it have some site. So if you have name for that, if you remember them already, the name of the website already, then it's okay. But in case if you don't remember, you can Google it, okay? So I'm going to Google it. So I'm going to type
Niraj,
here.
before you proceed, there's a question from Jerry about the resolution. What is the standard units for resolution?
Standard units for the resolution?
Yes.
So in case, yeah. So in case if you are obtaining the image in the digital sensors, okay, just like in case of our telescopic camera, it has the sensor. And as all of us know that each image is made up of very small, tiny element, that is, we can call it pixels, picture element. As we say that the smallest or the basic unit of life is cell, okay? So since we say that the cells and cell combines to form a tissue, and from tissue and tissue it combines to form organs, and then organ system, and then the whole body, okay? So you can also take it as a building block. Since the brick is the building block of the house, so we can say that the pixels are the building block of the image, any digital image, okay? So for resolution, we can say the number of pixels per inch, okay? Pixels per inch, PPI. You can say the resolution as PPI. So it is the unit. You can take it PPI in inch. If you wish to take in millimeter, then pixels per mm. But usually used is PPI, okay? Pixels per inch. So more is the pixels, so more are the number of pixels, so more is the resolutions, okay? So if we have, just imagine we have 10,000 pixels per inch, and another image has 5,000 pixels per inch, then of course the 5,000, so the image having the 5,000 pixels per inch will be much more clear, or have more resolution in comparison to the image which has only 1,000 pixels per inch. So can you get my answer?
Yes, I think that was a very complete answer.
So, okay, so I think we'll be discussing much more about the pixels in next Saturday. So we'll be playing with the things like the pixels and all. Okay, at that time we'll become much more clear. So shall I proceed now?
Yes, please.
Yes, thank you. So I'll write NASA online robotic telescope. So I have not used the word microbservatory. Let's see if it can find or not. Yes. So here is the result. The first very result, the observing with NASA, the microobservatory. Okay. So there are some others also, but we can choose the first one. So it will get you directly into the main link. So observing with NASA microobservatory, I will click on this site. So here comes the front page. Okay. So you can see okay. So you can see here over here controlling the telescope. Okay, control the telescopes. There are other projects and activities, training and resources, analyze the images. So there are many. Okay. Now to order the image, it is very simple. You can click over here, controlling the telescope, control the telescope. So it will get into the new window. So here we have choose the target. Okay, now select your target. The telescope will take an image of your selected target. But prior to selecting your target, you can click on the thumbnail to see the detailed view. Okay, so just take, for example, if you wish to capture moon, okay, you can just click on it and you can see thumbnail about the moon. So see here, moon, the distance is 384 kilometers. Okay, and there are some informations about the moon. Okay, like this. Yeah. So once you are confirmed that you wish to capture the moon tonight or maybe the next night, you have to click on this observe. Okay, so you can directly click to observe over here. Okay, so I have clicked the observe. Now there are some settings, okay, which needs to be adjusted. So adjust your telescope settings. The options you choose will be sent to the telescope and it will take your image tonight seeing these settings. Okay, so once you order the image, so it will remain in queue. For a person who have ordered the image before you, so his image will be taken first. Okay, then after it will come to your turn. Okay, so you have to wait for the images to be taken. Okay, but it will not take much more time. It will depend upon the number of requests. So here are some adjustment or say settings that we need to do first before ordering the image of the object. So here is the field of view. We have three very options over here. So one is the normal view. So 1 degree, this is the angular distance. So 1 degree. There is the another option, zoom view. So this is 0.5 degree, or you can simply see the image over here. So it will describe it easily. So if you click on the zoom view, it will give the zoom version of the image, but it will not give the 100% size. Okay, so it will be approximately, I think, so see it is not more than 60 or 70%. So this is not more than this is, I think this is 60 or 70%. Okay, so this is the zoom version, and this is wide view. In wide view, if you so this is used when you have to take the image of some other objects which is nearby to the moon. For example, if you know that let's say the Venus, okay, the Venus is adjacent to the moon tonight. Okay, so if Jupiter will be very close to the moon at some specific time as seen from your location, okay, tonight, then what you can do is you can choose for this, you can go for this field of view. So in that case, when you order the moon, then Venus will also come in this image. Okay, so if you want the wide angle view, okay, in this case you can choose this. So it is your so according to your requirement, what type of image you want to order. Okay, so I am just ordering this one, normal view. So neither too much small, neither too much zoom, so the normal. Okay, you can see the blue dot. So you have checked this dot. Now the exposure time. So what do you think? I have one question. So for moon, what would be the best or what would be the appropriate exposure time? So the first one is 0.1 second, another is 1 second, 30 seconds, and 60 seconds. So we have discussed earlier. So by 1 second exposure time, we mean to say that the light will enter inside the telescope camera, okay, only for 1 second. If you go for 60 seconds, then the light will enter for 60 seconds. So you decide first, what will be the appropriate exposure time for the moon? I want the answer from you, teachers. So
60 seconds.
60 seconds for the moon. Okay, any
Yes.
other options? From other teachers?
1 second.
1 second. Okay. Any other? Okay, let's see here. So it depends upon what phase of moon it is, right? So if it is the full moon, then we'll get more light from that. Yes, relative to the moon, relative to the half moon or the quarter moon. Yes, so it depends upon the phases also. Just assume it is the full moon then. Okay, so what do you think? 60 seconds is not much more enough. So the moon is the most bright object seen in our sky during night times. Okay, so after sun, it is the moon which has so much brightness in the night sky. So when the light will come from the moon and it will expose, when it will hit the camera sensor for 60 seconds, I think the image will be overexposed. But let's just try. I'm hitting 60 seconds. Let's say what's the response. So it says that image may be overexposed. Okay. So if you hit the options which is not appropriate for you, then the NASA Microbservatory will tell you that you know the correct or appropriate options to choose for. Okay. So 60 seconds the image may be overexposed. Okay. So one of our teachers have told 1 second. Let's try 1 second. So 1 second is also overexposed. Okay. So just take the small one. 0.1 second. So let's see here. 0.1 second is the optimal exposure time to capture the moon tonight. Okay. So you don't have to remember all this. So it is very helpful. You can get the appropriate settings. Okay. Now there is another option, the filter selection. First of all, I would like to say something about the filters. So why the filters are used. Okay. So what happens when we see the object that is not colored, like the moon. Okay. So what is the color of the moon? So the moon has both the shades of gray and the white. Okay. Yeah. So it is just the black and white, like black and white. Okay. But what is the color of say some galaxy, some nebulae? So we must have seen the image of the galaxy, the Milky Way galaxy, the Andromeda galaxy, some other galaxies, and the nebulae like the Orion nebulae. Okay. So what we have seen in our textbooks, they are multicolor. They are very beautiful objects to see in the night sky. Okay. So there are many colors. Okay. So, but what happens in case of the camera we have attached to the telescope? So the CCD camera can't capture the colored image of any object at a time. So we have one process. So there are several filters. Okay, the different filters like the red filter, the green filter, and the blue filter. So I think all of us have some idea about the primary colors. Do you have idea about the primary colors? The RGB?
Yes, yes.
Red, yeah, G green.
Yes, yes.
Yes. So when the primary color gets mixed up, we can get various other colors from that. Okay. So from the combination of red, green, and blue, we can get the various other colors. But not confused with the painting. Okay, so if you will paint red, green, and blue, then I don't think it will give the correct combination. So here the combination of red, green, and blue is according to the frequency of the light. Okay, so the primary colors, the combination of red, green, and blue by the combination of frequencies is much more different than coloring with the watercolors and the poster colors, right? So okay, so primarily we have the three filters, the red, green, and blue filters. So when we are using the red filter, it will allow only red light to pass through it. Okay, So the image, the final image will be of which light? The red light. Okay, the frequency that is equal to that of the red light. If you are using the green filter, then it will allow the green light. Okay, the frequency of green light, and same in the case of the blue filter. Okay, so when we take the image of an object in these three different filters, red filter, green filter, and blue filter, so there will be three different images. Okay, and when we get these three different images, we can use the image processing softwares like the Salsa-J. We can use JS9. Okay, so we can use this image processing software to make a RGB image, the colored image. Okay, from three different images taken from with the help of three different filters. Right. So we'll talk about that on later sessions. So here we have only one option, that is the gray filter. So we have only one option for the filter selection for the moon. So can you guess why it has only one filter for the moon? Why not the red filter, green filter, and the blue filter?
I would think it is because the appearance of the moon is normally grayish, so that it will allow that gray light to push through.
Very good. Yeah. So since the image of the moon is not multicolored, yeah, so it doesn't have any red, green, and blue. Okay. So what we can see is it is just the white and black, or we can see the gray. Okay, the gray and whites. Okay. So we don't have any colored filter for that. So you are absolutely right. So we have only the gray filters. So we can use the filter to cut off the unnecessary light. We can also use the UV filters to cut off the unnecessary lights, but that is another thing. So I'm just clicking to this gray filter. Okay. So now all the three settings are checked. Now I will
excuse me, sir.
Yes.
Excuse me, sir.
Yes.
Maybe before we move, look at the second, can I say, panel in the middle.
Okay, exposure time.
Exposure time. The exposure time.
Okay.
I was just wondering.
Yes.
When you said that the exposure time would be dependent on the phase of the moon. What would happen when it's not full moon and the moon is actually not there? Is it possible to see?
Yes. So what I think, these four options are not for the different phases. Okay, so I think if you have full moon as well as if you have quarter moon or half moon, I think 0.1 second we have to go for this option. So there is very slight change. Okay, so there is very slight change in the exposure time. So of course, if there is full moon, then we have to reduce the exposure time. If you have the quarter moon, then we have to increase the exposure time. But that increment is of the second digit after decimal places. What I think that, okay, so I have ordered the image of the moon of different phases, but what I have found is at all the time they take this exposure 0.1 second. I have not found the website taking 1 second or 30 seconds or 60 seconds. So I think 0.1 second works for all the phases, the full moon, the half moon, the quarter moon. You can try yourself, but as per I have tried, as per I have the experience with this website, I think for all the phases of the moon, we have this 0.1 second as optimal exposure time.
Okay, thank you.
Thanks. Yeah. Okay, so
excuse me.
Yeah.
Assuming you clicked 1 second exposure time, is it that you would not be able to see the moon?
0.1. Can you repeat the question? What if you say that? Yes.
Assuming you clicked 1 second time of exposure.
Yes, 1 second.
Is it that you would not be able to see the moon?
Yeah. So what you will see is on the final image that you will receive in your email, so you will see the moon, but the boundary of the moon, but the surface of the moon is not much more clear. It is overexposed. You will see much more light coming from that area. Okay, so the overexposed means that.
Okay, okay, thank you.
Okay, so you can, I think we can't try because it will not take this option. So if there were the facility that we could take the exposure time of 1 second, then we could easily see that what the image will look like, but unfortunately it will not allow for the overexposed options. So we have to go for this 0.1 second only. But we can try if you have the DSLR camera, because the DSLR camera has also various functions like changing the exposure time. Okay, it doesn't have option for the filter selection, but we can try to take the image, to capture the image by changing the exposure time. Okay, so if not, that's okay.
Yeah, following your discussion.
Yes.
Following your discussion.
Yes.
You say that the moon is the second brightest object in the sky.
In the night sky.
And,
yeah.
And that's why the exposure time has to be small. But at times I observe the moon during the day. So if you observe it during the day, therefore, would it mean that the exposure time would have to be increased?
Yes. So when I say the moon is the second brightest object, it means that the relative brightness, okay? So it doesn't mean that the actual brightness of moon is much more than the stars, okay? So since the star, we all of us know that the star has much more light, it is much more bright, okay? But since the stars are much more far away from us, it is more than hundreds and hundreds light years far, so the brightness of the stars decreases, the apparent brightness. Yeah. So if I say the apparent brightness of the moon, then we can say the apparent brightness of the moon is more than that of the star. Okay. Yes. So when you are talking about we can see the moon at the daytime. Yes, we can see the moon at the daytime. But when you are going to capture the moon at the daytime, what we will find that the light from the surroundings also gets captured. Okay, and you will not get much more details. Okay, of the image. We can take the image of the moon at the daytime, but we have to play with the exposure time and other settings. Okay, we have to balance all the settings carefully. So it is sure that the light from the background will affect the final image. Okay, so we have to try it taking the image of the moon at the daytime. Of course you can, but you have to play with all those settings.
Okay, okay, thank you.
Okay, welcome. Yes, so should we proceed? Now I'll proceed to continue. Well, so the next window appears. So here is, we have to put some informations so that we will be able to request for the object. So first of all, we have to provide our email address. Well, I am providing mine. So I have been using it previously, so I don't need to write it down. So email address. So you can see I have provided my email address. So we have the is, okay. So, okay, we can put the is group. Now it is asking for the gender. So I have to choose the gender. So it is asking about the state. So all of these are the states inside the United States, okay? So since we are outside of the United States, we can just click this one, outside. Now, there is a question, how often you have used this telescope? So it's up to you. If you are using the first time, you can click over here. I have used it more than 10 times, so I'm clicking over here. So how would you rate your astronomy knowledge on a scale of 0 to 10. Okay, so 0 to 10, it is not good to just myself. Okay, I'm giving it my astronomy knowledge to 6. Can't click to any options. So may we contact you in the future about the microobserver that we use. There is some noise from the background. Can you mute off the camera? Please mute the mic. Yes. So it is up to you. If it is asking for that they may contact you in future about the micro observatory use. Okay, I'm hitting yes. Now I have filled all the informations they were asking for. Then I will hit this submit button. Yes. So see here, your request for the telescope image has been submitted. So here are the settings that will be used by the telescope to take an image. So now this is the distance of the moon. We have selected the field view as normal. We have selected the exposure time as 0.1 seconds. And we have chosen this gray filter. And I have provided the email address. So just read the information carefully. So tomorrow or the next day, you will receive an email notification from the Microbservatory with the link to download your image. Okay, so maybe tomorrow or the next day. So usually it sends image within the 24 hours or within the 48 hours. It doesn't take much more longer than 48 hours. So it will send you the image back within the 48 hours. So to see the recently taken image, you can also go to Microbservatory image directory. So the image you have clicked, the image which are frequently clicked or the ordered are kept inside this archive, okay, the image archive. But you don't have to do that. You will directly get the image in your email, okay? So I think you don't have to do with all these options, okay? So finally we are done, and we have to wait for 24 hours or maybe 48 hours. So they will send back the image. Okay, I'm going to show you how they say the image in your email. So I have previously ordered the image of the moon. I don't know, it was 2 weeks or 3 weeks back, but I'm going to open the email and will show you. Okay, I'm searching. Okay, I have got email from Microbservatory. It is not of 2 days, but I have ordered it few weeks ago. So see here, the email will look like this. So there is like a reply, telescope image from the Microbservatory, and our observing with NASA image on the Orion Nebulae M42 are ready. So I have ordered the Orion Nebulae. Okay, so it is the nebulae which lie in the constellation, the Orion constellations. We'll talk about that later on. So look here, we have 4 different images. Okay, so one is the SSO red filter. So this image has been taken using the red filter. The next image was taken using the green filter, and the third one was taken with the help of blue filter. And there is one more additional image. So I think you won't be able to see any object. So actually this is the dark filter, okay? If you want the final result, if you will do the image processing, and if you wish to get much more clear image which is free of the noises, then we have to do the dark sky calibration or the dark image calibration. So it is not of use for the normal people. So if you want to go in advance, then you will want this dark filter, okay? So here I have got the 3 filters. If I click on this view, so there are much more details on this. I want to go back. This is your, okay. So here is large form. So there was the information, and look over here to save this image in the high quality FITS format. So FITS is the extension. This is the file extension for the image, particularly used in the astronomy. So its full form is Flexible Import Image Transport System. Okay, FITS fits Flexible Image Transport Systems. So this type of image files are much more important in the field of astronomy. They are the large file, and that contains much more information, many informations, okay, in comparison to the JPEG. So have you heard about the PNG, the JPEG? They are the commonly used image files, okay? But the astronomical images, they are commonly taken in the FITS format, okay, FITS format. So we'll be learning much more about the FITS FITS file during the image processing, and maybe on another Saturday when we'll be doing much more advanced of the JS9, okay? So at that time, and also during the CELSA-J, we'll be working with this FITS FITS images, okay? So to save this image, I have to click to save this image in the high quality. Yes, I want the high quality. Click on the following link. So you can see the link over here. Well, I will click on this link, and yes, you can see here. So it has been downloading, and it has been downloaded. You can also see in the, okay, so here you can see the image has been downloaded. I will copy it. I will paste it somewhere, maybe on my desktop. So here we have, okay, I will make one folder. I will name it as Orion FITS image. Okay, I'll keep this fit file inside the folder. And one more thing, if you double click this one FITS file, you won't be able to open. Okay, so like this, you won't be able to open. Okay, so but where in case of JPEG image, if you will click or double click on the image, you will be easily able to open the image, right? So this image can be opened only using the image processing softwares, okay, like the CELSA-J, the image, the JPG, the JS9, okay, and there are many image processing softwares that could be used to open this type of files, right? So I'm moving back. So it was of which red filter? Yeah, so I'm getting back. I'll also download. Sorry. Yeah, do the same with the green filter. Okay, this is for green filter. 2, 4. And again for the blue filter. I think you can do this. I will not spend the time for this. Now let's try for some other objects. Let's try for some other objects like controlling telescope. Okay, control telescope. So let's choose any deep sky objects. You can select from this one. So let me know which object you want to add. Okay, I think all of us are familiar with this Milky Way, right? So it's our galaxy Milky Way. So just observe. And there is only one option, the wide view option, as the galaxy is, this is of very big size, okay? And it is far distant, okay? So we can't see the zoom version using this telescope. So we have only one option. So I'll check on this. Okay, can you try for the exposure time? Which exposure time do you think it is appropriate for the galaxy?
60 seconds.
I think 60 seconds.
Okay, 60 seconds. Yes. So it is the optimal exposure time and no filters. I think there should be a filter for this, but I don't know why they have not kept any filter for the Milky Way galaxy. Okay, so if you have only one option, then you can go and hit to the continue. Okay, but I'll choose the another option. Okay, I want to show you about the different filters. So okay, I will do any crab nebulae. Crab nebulae. Yes. So crab nebulae, it is 6,500 light years. Okay. So it will take light to reach from crab nebulae to us on the Earth on 6,500 light years. Okay. So this is very, very far away from us. So it will take 6,500 years for a light to travel from crab nebulae to our Earth. So it has only one view, the normal view. Okay, normal view. And the exposure time, of course, I think it would be 60 seconds. Yeah, 60 seconds. So here, yes, you have filter. So if you don't want any filter, then you can click on no filter. If you want only red filter, then you can click on this. But for a good reason, I'm not going to click this one, neither this. I'll click on the multiple filters. Okay. So if we will have multiple filters, that is, we will get 3 images all from different filters, and it will be much more fun making the color image of this crab nebulae. Okay. So you just continue it and do the similar steps and you can perform this. So I think it was very easy, but it is much more interesting to have the image of your own. So you are not using the telescope manually, but I think the image the copyright of image. Okay, so it belongs to you. So it is your image because you have ordered it. You have used your own settings. Okay, so this is the property of yours. So no one can claim on this image. So you have ordered the image. So this is your property. So it's just like taking the image with the real telescope. Okay, so just the method is online. You have to control it online. Okay, but it is just like taking the image with your own telescope. So this is completely free. Okay, it has been developed mainly for the students, for the educators, for we teachers, and it is very good to have the image of the desired objects for those who don't have special equipments like the telescope, like the cameras. Okay, so we can do astronomy quite easily if we have the image. Once we have the image, we have we have more informations. We can have much more informations from that image, and we can do image processing to do many researches as well as. Okay, so the astronomers, the scientists often use this method. This is the similar method. Okay, so they also use this method to get the image, and they do the image processing. They come to some conclusions. Okay, and they make some findings. So this is the way how the astronomers work. Okay, so now we are also the part of it. We'll teach our students to use this online telescope, get the images, and in our next session, we'll be doing some activities related to processing the image. Okay, so I hope all of us have get through this, and I'll say that you can try it just now. So will we want some break or what? And you can try yourself with the same process.
Hello, Niraj.
Yeah.
Suppose there is a live event, let's say something like an eclipse.
Eclipse, yes.
And I would like to capture that event in real time.
Yeah.
Is it possible to use this telescope?
No, so I have also tried this. I have had the same question like as you asked me. So during the eclipses, so there are many requests, okay, at the same time from the different users. So at that time, you won't get your image requested as for the same time and as for the same day. Okay, so it is very difficult. I think if you are lucky enough, then you will get the image of the eclipses and all. But
okay,
I think, but I'll suggest you to try it once. Okay, try it once, and I think most of the users will do the same. So during they want to capture if it is solar eclipse, they would be like capturing the sun. If they have the lunar eclipse, they would be like capturing the moon. Okay, so if we have multiple requests from different persons, then I think that it is better to find the image in the image archive. Okay, so in the archive they will put the image which has been frequently requested. So although if you won't be able to make any request, you can search in the image archive, you will get the image of the eclipse. I think it will I think we can do that way.
Thank you.
Yeah, thank you.
Yes.
Is there a possibility of taking an image at some specified time? I didn't see the time setting here.
No. So you are not allowed to set the time, right? So it will click the object when it comes in its range. So if just take an example, if you want to capture the moon right now, let's suppose the moon is below the horizon. Okay, let's say that moon has not risen above 0 degree. It is below the horizon. then it will wait for a moon to come up. Okay, so it will decide it's the appropriate time, and when the moon is quite up from the horizon, and the atmospheric conditions are good enough, then it will take the image of the moon. So you can't specify the time as per your wish. So you can just make the guess. So if like that, we have eclipse on tomorrow, then if I'm ordering the image of the sun, then probably I'll get the image of the sun for tomorrow. So I'll have the hope. Okay, so I'll have that hope. So it will not say that it will take the image of tomorrow eclipse, but still we can try like that. Since it is so, since they capture and provide the image within 24 to 48 hours, so it is, so there is much more probability that it will get the image the next morning or the day after that. So we can only hope and do the probable expectations, right?
Okay, thank you.
Thank you so much.
Hello, Niraj, once again, is it possible to take images of two objects at the same time?
Since we are not allocating that, we don't have access to provide the time, so you can order the two images, yes, but it will capture, it will take the two images at some interval of time. So they will not say that the image has been taken at this time or that time. I don't know, but I think if you read all the informations, they have or they have not included the time at which the image has been taken. I have not seen much more in detail, but we can make sure that the two images can't be taken at exactly same time. So they have to be some gap or the interval in between them. Yes, you can order any number of images. You can order 5 images just at a time, and it will provide you the image. It will capture the image according to the its convenience, according to how and when the object will appear high above the horizon at the night sky. So they will decide. So they must have some algorithm. There must be some programming done in that robotic telescope, and they will decide when to take the image. So yes, we can order the multiple image. Yes, we can do that.
Thank you.
Thank you so much.
Yeah, thank you. You had posed another question whether we could go for a break. I think Santos, it would be nice if we would go for some 30 minutes break.
Yes, I think we can take some break. Okay, so